Hi everyone, this is the lecture 2 on chapter 4 about for optimum receiver. In this lecture 2, we're going to we plan to discuss about the waveform and the vector adaptation channel. And as we have described in the first lecture, that any optimum receiver contains what? Contains two major parts. The first part is the demodulator, and the second part is the detector. Okay, so the any kind of the digital communication receiver, it maybe looks very complicated, the architecture is very complicated, but if we fundamentally we can the receiver can be represented by these two parts. The first part is always a demodulator that convert the transmit signal into a vector, and the second part would be do a detection based on the vector and do an estimate of the transmit symbol. That would be the MAP or ML detector. Okay, so that's what we going to have for this lecture 2. Okay, and again here we further discuss the optimal detector, and here we are not assuming any kind of modulation type yet. Okay. Okay, that's the begin with the waveform, the received waveform, that is RT. Say the received waveform is RT. Here RT means that this that can be represented, decomposed by the n-dimensional basis. Okay, can be do the projection onto the signal space of n-dimensional signal space as that described by the transmitter. So the received signal here, that would be first we do the inner product with each basis, phi 1t, phi 2t, 2 phi nt, do the projection onto each basis, right? Then on each basis we will have R1, we will have R2, and we have Rn. That is the projection component onto each basis. Then we have together we have the vector R, and the vector R would be the input to the MAP detector. Then we have the estimate of S. Okay, so the so-called correlation demodulator, okay, that is to identify the correlation of the received signal, right, with each other. This inner product or this projection, that is also called the correlation demodulator, because that is the correlation of RT with phi 1, phi 2, and so on. This correlation of the received signal with each basis, for k equal to 1 to n. Okay, so Ri would be the component. I would be the component for RT of the projection. Here the inner product is is over the symbol time, is the definite integral from 0 to t. Okay, and the RT contains two parts: the transmit signal ST and the noise NT. And then there will be the I from 1 to n are different. There are n components of Rn. So the first part is called the demodulator, and the second part is called the detector. And here we have the MAP detector. Any type of the receiver, the architecture contains these two parts, demodulator and the detector. So the receiver architecture generally contains these two parts. In general, any digital communication receiver architecture that will contains these two parts, the demodulator and the detector. And here we have the correlation with the basis, the projection, and this type of demodulator is called the correlation demodulator. Okay? And here we discuss another type of demodulator is called matched filter demodulator. That's defined. What do we mean by matched filter first? What do we mean by matched filter? For a signal ST, okay, say this is ST. Say this is ST over the time period of t. Say this is ST. Like we have a simple waveform that is ST. And if we passing this ST through a filter HT, HT, okay, HT would be equal to the ST minus T. Okay, it looks like this. It's the flipping, okay, it's a flipping of S, right? Flipping of S to the other side, and the shift, flipping this negative T, that is means we have a flipping over, right? It's a mirror flipping, and the shift to the right for capital T. So that would be HT. This HT is called a matched filter for ST. It's a matched filter because it's matching to ST and is actually a mirror. It's a mirror to ST. And if we pass this ST to this filter, okay, to this matched filter, okay, we pass this filter, and what will we have at the filter output? That means that we have a convolution, right? Have a convolution of the input signal with the filter impulse response, right? Have a convolution of ST to the impulse response. As we can see and know about the convolution, what do we mean by convolution of two functions? The convolution of two functions is by, again, we will flip this edge, right, to the left, right, and then pull it over, right, at t equal to 0, that we have flipping of edge to the right, to the a flipping of edge that would be this would be similar to ST. If we do a flipping of HT, right? So that would be the t equal to 0, and then we pull this over. When t equal to, when the integral of t equal to capital T, right? Then this match filter and this S, right, would overlap completely at t equal to capital T. Then the integral have the maximum value, all right? And when t equal to greater than t, then the overlap area becomes smaller and smaller, and then we then become then after 2t, then they are not overlapped. So the output will be look something like this. Okay. So if we so in here at the filter output, if we take a sample, okay, if take a sampling at this is yt, right? If we take a sampling at this time t equal to capital T, right? If we take a sampling at the integral, then this fully overlap, and then we have the maximum value occurs at t equal to t. Okay, that is match filter. Okay, now we apply this match filter for the demodulator. It's like this. Then the receiver here, we have the receiver here, and here the match filter HKT equal to that matched to each basis function. That matched to each basis function phi kt. That is phi k capital T minus T. That is by that is the causal matched filter. Okay, and at the match filter output, we do a sampling. Take the sample at t equal to capital T, right? Remember when we take a sample at t equal to capital T, and what will we have? We will have the maximum value, right? We have the maximum value at the matched filter output. Okay, let's take a look at each match filter output here, YKT. The match filter output, that is the R convolution with HK. Here, R convolution with HK. And here HK, right, because HK is the match filter to phi. So this HKT minus tau become phi k T minus T plus tau. Okay, that's the match filter output. And is okay, and is this match filter demodulator equivalent to the correlation demodulator? If we take the sampling, okay, if we take the sampling for t equal to t here, okay, if we take the sampling here, t equal to t, that is this t equal to capital T, that is this t equal to capital T, right? So this the sampling output yk capital T, that become R times, right, phi tau and the d tau, the integral. And so what is this? This is what? This is actually exactly the same as the demodulation correlation demodulator, right? It's the equivalent to the projection of the received signal onto the basis, phi k, right? They are it is exactly the same. It is exactly the same. Okay. So the match filter demodulator is equivalent to the correlation demodulator. They actually equivalent, but the implementation is different. implementation is different because this because this is the way we do the implementation, that this is just a filter and this sampling is just a flip-flop in the implementation. Here we're trying to show that, okay, now we have shown that the decorrelation demodulator and the match filter demodulator are equivalent, right? And next we're trying to show that this type of match filter demodulator will maximize the signal to noise ratio of the demodulator output. That means that, and why we are trying to show this, because when we maximize because the demodulator output, demodulator output goes to the input of the detector, right? Goes to the input of the detector, and so the SN ratio of the detector input would affect the performance of the detector, right? The higher the signal to noise ratio of the detector input, the better the performance. The better the performance of the MAP detector. So, and here we're trying to show that actually the match filter demodulator will maximize the signal to noise ratio, and hence, and therefore would improve that prepare the signal that would be best for the MAP detector. Here we have the receive signal RT, okay, that is equal to ST plus noise NT. Where this noise is, let's have the signal model first. This noise has the is the AWGN channel, and S is confined within the symbol type of capital T, and the signal to noise ratio of YT. We're trying to show that the signal to noise ratio of YT would be maximized. If this HT is matched to this transmit signal ST. Okay, let's look at this receive signal first. This receive signal YT is the convolution, right? Again, is the convolution of the receive signal and the filter H, and the filter and the match filter H, and this receive signal contains two parts. That is the transmit signal and the noise. So that this contains two parts. And then in this match filter architecture, that after this match filter, we do a sampling at T equal to capital T. Okay, we do a sampling, right? What we do after this match filter is a sampling. And then we have this Y capital T, that's T equal to capital T. So here we have YT, we have Y, we have Y capital T, right? That means so we have all the T equal to capital T. We have all the T equal to capital T here. And look at, and so at this sample Y capital T would be the input to the MAP detector, right? This would be become the input to the MAP detector. And this signal Y capital T actually contains two parts. The first part we call this YST, that would be represent the signal part. And the second part we call it YNT, that would represent the noise part of the sample. Okay, the sample contains two parts, the signal and the signal part, and the noise part. Okay, and here we're trying to analyze is what the signal to noise ratio, right? So that would be the power ratio of the signal power and the power to the noise power. That would be the signal to noise ratio. Let's take a look at the signal to noise ratio. By definition, the signal to noise ratio is the ratio, okay, of the signal to the noise power. And the noise part, okay, the power of the noise, right? The power of the noise is the because the noise is a random process, right? This is when we take the sample. This sample is a random variable, right? It's a random variable, and the power, the average power, the power would be the autocorrelation function with the DC value of the autocorrelation function, right? That would be the average power of the noise. Okay, so here we have the YNT here. That we have the formulation of YNT here. That and the first two. Here is the noise random variable at tau 1 and noise random variable at tau 2, and here is the function of the H into the double integral of the convolution. Okay, as we know that this noise, the correlation of noise at time equal to tau 1 and tau 2, the noise are independent, right? Noise are independent, and because it's Gaussian, right? So that the correlation of these two noise has value only when tau 1 equal to tau 2. Only when tau 1 equal to tau 2, the correlation has a value, and the correlation would be n0/2. Okay, so this would be equal to n0/2 times the delta tau 1 equal to tau 2. Okay, so that becomes the correlation becomes delta function. So this product this delta tau 1 minus tau 2 and this h tau 1 and this h tau 2, it has value. Okay, it has value only when tau 1 equal to tau 2, right? Otherwise, this delta would be 0, right? So these two functions, the product of this h tau 1 and this h tau 2, only that this product has value only when tau 1 equal to tau 2. So that tau 1 equal to tau 2 equal to tau, so that becomes h squared. So that would be, that becomes the power of noise. The power of noise. So we have the power of the noise here, and here the power of the signal. That would be what? That would be the sample at the match filter output at t equal to capital T. And here we, by using the Cauchy-Schwarz inequality here, right? Remember, this is a square, the inner product of the square function, the square product, and by this Cauchy-Schwarz inequality here, this square would be less than the product of the separate product. If we consider this is two known, let's recall this Cauchy-Schwarz inequality. The inner product of two functions, the inner product of two functions would be less than the length of each vector of each function, the length of each function. So that is the Cauchy-Schwarz inequality, right? So, and this equality, the equality holds when this function g1 and g2 are parallel, or they are just a scaling of the constant, a scaling of the constant, right? So we have this signal to noise ratio would be less than would be less than this formulation, okay? And here this one and this one, right? This term and this term are equal, right? This and this are equal, so that so we will cancel out these two terms. This integral and this integral are equal, and this is what? This is the signal energy, right? Signal energy. So this is E, right? This E. So the overall, the upper bound of the maximum of the signal to noise ratio becomes that 2E over N0, right? 2E over N0. That would be the maximize of the SNR. So when does this SNR would be equal? The equality holds here. Look at here. When G1 and G2 are parallel, or G1 and G2 are the same in just a scaling. So this equality holds when this S, okay, this S equal to HT minus tau. This S tau equal to HT minus tau. They're just a scaling. Then we have the maximum, right? So when that is when HT equal to the match filter of ST. Okay, when HT equal to the match filter of HT, then we have the maximum of SN ratio. So here we have conclude that by using the match filter of the correlation demodulator, that will maximize the SN ratio to the input of the detector. Okay, so the next we plan to discuss the MAP. After we have the demodulator, we will have to the signal goes into the detector. It goes into the MAP and the MAP detector. Let's see what happens if we have the this signal to the MAP detector. Now here we have this received signal R, right? Received signal R that has the after the matched filter. Okay, this R here. Okay, this R here is after the matched filter, right? After the matched filter that we have we have this vector R, and based on this vector R, we're trying to determine or estimate the received signal, the candidate, which transmit signal was transmitted, right? That maximize this conditional probability. Then we have this final estimate of the received signal. This process, the concept of the MAP detector is similar to the Cinderella story. Remember, this is Cinderella, right? And Cinderella has lost her shoes in the party, right? Lost in the shoe in the party. The Cinderella is the S, and her shoe is the R, is the clue. Okay, and we are trying to find from the many possible candidates. S1 to Sm, we are trying to find which candidate that best fit to the shoe. So the shoe is the received signal that we have. The shoe is the received signal what we have, and we try to find who owns the shoe, which candidate has the best, which candidate has the best fit, okay, to the shoe, to our clue, and the candidate that is most had the perfect fit, that has the highest probability. Okay, that we mean that then we have the highest probability. Then we make a decision. Okay, make the decision that this is the estimate. This is the estimate of our decision of the candidate of the transmit signal, and in this way, then we have the optimum that will minimize our error. Okay, and so this conditional probability would be based on this received signal R. Okay, and this formulation, we can rewrite this formulation by the basis theorem and the conditional probability on probability R with joint probability of R and S, and the joint probability could be we could rewrite this joint probability to PS times conditional probability on S. Okay, and because this PR is the summation of all possible candidates, right? PR is the summation of all possible candidates, so it's irrelevant to the S. Okay, so the S that maximizes this ratio is equivalent to S that maximizes this product. The way we're doing this is sometimes this conditional probability on R. This is called posteriori probability. That is difficult. That's difficult to find. We don't know. Given these shoes, we don't know which candidate has higher probability. Given these shoes, we don't know who has the higher probability. But given the probability of S, given the probability of S the probability conditional on S. This is easier to find. This is available. This is usually available, and this is not available. Okay, and here if we assume that this PS, this is the prior probability of the source, the prior probability of source, and usually we have no idea which candidate is more likely, right? This is equal right society, right? So each source has equal probability. That is, everyone has equal probability of 1 over n. So this PS, in this case, equal probability assumption, then this PS would be irrelevant to the decision. Okay, and then with this equal probability assumption, then this detection scheme, that would become this conditional probability on S. Conditional probability on S. And this is called the maximum likelihood detection. It's called the ML detector. Maximum likelihood detection. So with this equal probability assumption, this posteriori, this MAP detector become this ML detector. Okay, look at this difference. This conditional probability are different. Would be that become this conditional probability of each source. Conditional probability on each source. How to find this conditional probability is a different story. Given the channel, given the probability model, given the signal model and the probability model, what type of modulation, what type of channel, what type of the noise, the Gaussian, then we can find this conditional probability. Okay, and then with this conditional probability, then we can do this argument and define the optimum detection. And this is called the optimum likelihood, the maximum likelihood detection. Okay, and here, okay, so here this conditional probability is called the likelihood function. It's called the likelihood function. Likelihood function, that means that the criterion, like the criterion that we use to make the decision, is called the likelihood function. Okay. The way we are doing this is because in most cases, usually this MAP, this function is not available. Is not available. We do not know this conditional probability, but this conditional probability is usually available or subject to the channel model. It'll become clear. We will show you how to find this probability in the next lecture about given the example of the modulations and the channel model. Then we'll show you how to find this likelihood function. Let's do an example for the NTHU channel. If this channel is an NTHU channel, say if this is an NTHU channel, say this is an NTHU channel, then we have the channel probability model, right? Then we have the channel probability model. Then the received signal, okay, R is the vector is R plus noise. The noise is an Gaussian noise with zero mean and the variance of n0/2. And S here we assuming this transmit signal is equally probable. Okay, and for example, this receiving, for example, this so that's the received signal. Say this is the transmit signal. Say this is the transmit signal, and that is at the transmitter side. That is perfect on the constellation. And the received signal that with the noise that would spread out around the transmit signal, that and this would be the received signal, right? That the signal plus noise. If we receive the signal many times, then we have this kind of the received signal. And we're assuming that every transmit symbol are equally probable. Okay, so here if we apply the MAP detector, okay, because why MAP detector become ML detector, right? Remember what we have say, because when SM is equally probable, when SM is equally probable, then it's become ML detector. Okay, then we have this detector become ML that is based on the conditional probability of S. Okay, and now we have this probability model, right? We have this probability model. Then, given S, given one of the S, right? Given one of the source S, right? Given one of the source S, and the received signal, right? The received signal would be a Gaussian distribution because it's the AWGN channel. So the received signal is a Gaussian distribution with mean value on the transmitted signal, right? The probability distribution, of the received signal is the Gaussian distribution. The probability distribution is a Gaussian distribution with mean value on the source, on the depends on which symbol source is transmitted. Then the received signal would have the mean value on this source, and so given one of the source symbol, and with the received value of the received signal R, right? Then we can find the probability, right? We can find this probability, right? So R and R given R and try different S, we can find the probability. And so with this R is available at the receiver. The value of this R is available at the receiver, and we try different S. We can try different candidate S here, and then we can have the probability distribution for each candidate, right? Then we can compare the probability of each candidate, okay, probability of each candidate, and see which one is the maximum, which has the maximum. Then we can identify the which candidate is the most likely, the optimal candidate. Okay, and by doing this, we need to calculate we need to calculate this Gaussian function for each source. That would be complicated. So this calculation would be equivalent to this ln function. This ln function is called log. We just take the log function on this likelihood function, take a log value on this conditional probability, because it's ugly. The calculation is complicated. So we can do a log function. It's called log likelihood function. Then the result would be equivalent. Why the result is equivalent? Because because log function is a monotonic increasing function. Log is a monotonically increasing function. So any s that maximizes this likelihood function would also maximize this log likelihood function, right? Any s that maximizes this would also maximize this log likelihood function. So we will have the same detection result. But however, it will make the computation much simpler. We only need to compute the argument in the exponent. That would be this. That would be the which s that maximize the exponent. Right, and this would be that maximize this exponent. It would be equivalent to find an s that minimize the distance, right? That minimize the distance. Now, that is that find an s that has the minimum distance to the received vector. That is most likely likelihood. The minimum distance to the received vector. That would be help us to make the decision. So this is called the minimum distance detector. The minimum distance has an assumption. So when can we do this minimum distance detector? It is when we have this AWGN channel model. Then this ML detector become MD detector. Okay. And also, if we have further assumption that this symbol energy are constant, if the modulation, if the transmit signal, the energy is a constant for any m. For example, like MPSK, all the symbol has the equal energy, right? If the modulation does not have equal energy, then this does not satisfy. However, if this is satisfied, you can further reduce this distance calculation. Okay, because the distance calculation, that is this is the distance calculation of two vector, and because the equal distance, we can remove this, right? So that becomes the maximize the inner product of these two vector, of the received vector and of each source. Okay, so the detector become even more simpler. So this is called the maximum correlation detector. Okay, so with different conditions, the detector can be reformulated. Let's review it again, doing a quick summary. The original, we have the optimal receiver, we have the MAP detector, and if the channel is the Gaussian distribution, if the channel is equally probable, then this MAP become ML detector. Okay, and this ML detector become this minimum distance detector if we have the AWGN channel. If we have the Gaussian distribution, then this ML detector become minimum distance detector. And further, if the symbol energy is a constant energy signal, then this minimum distance detector that become this inner product, the correlation detector. Okay, so when we apply different types of detector, there's different complexity, but you have to be careful about the condition. The condition has to be the condition when we can apply this different type of detector. There's a condition need to be satisfied first. Okay, and okay, then this will be the all we like to share and discuss for lecture 2. And in the next lecture, we will see you on the next lecture for the optimal detection and further discussion on different type of the modulation. For now, we are not doing any assumption. Okay, we are not doing any assumption of the modulation types. So in the next lecture, we're going to apply different type of the digital modulators and see what